Okay, so what I have here is the famous or infamous DX7 synthesizer, which uses a synthesis method called frequency modulation, and it's implemented digitally in this instrument. So in this little video, let me just show how to create some simple sounds using FM. So let's start from the beginning. Let's initialize the tone. I click function and press voice in it. Yes, yes. Are you sure? Yes. So what I get is it's tone like this. It's a sine wave. Sine wave is a very unique tone because it's a very basic tone. It doesn't have any overtones. That's why it sounds a little muted. It's just a fundamental. It's not bright at all. It's a very muted sound. I'm going to turn off all the other oscillators here because the instrument has 6 of them. I just need 2 for my little video. It's simpler that way. I'm using algorithm 1 also, in which the first oscillator, called in Yamaha speakers called operator, but it's the same as oscillator. So let me just use the name operator from now on. The operator 1 is a carrier, which means it produces audible sound, the sound we can hear, the sine wave. In the algorithm 2, in algorithm 1, the operator 2 is the modulator. So let me turn on the operator 2 right now. Let me select it, and let me bring up output level of the operator 2. Now to edit, output level, and see what happens. I'm just changing the frequency of the modulator right now, and the sound is getting brighter and brighter. It's because the sine wave, it's getting bent at an angle, so it becomes closer and closer to a sawtooth wave. That's why the sound becomes brighter and brighter. There's more overtones. So what I'm going to do now, I'm going to change the frequency ratio of the operator 1 and operator 2. Right now it's 1:1, so both operators have the same frequency. But now, if I change the frequency of the operator 2, press the frequency course, and I'm going to change it to twice as high as the operator 1. See what happens. Now it's the same. It's twice as high, 3 times as high, 4 times, 5 times, 31 times. I just settle on 2. So now the ratio of the operator 1 and operator 2 is 1:2. Sounds a little different. Let's decrease the output level of the operator 2 a little bit. We get the clarinet-like sound. It doesn't sound like a real clarinet, but it's a clarinet-like. That's the qualities of it. Okay, let's modify the sound a little more. Now the frequency is 1:2. The frequency ratio of operator 1 and 2 is 1:2. Let's change it to make it not the even number. So that's going to create some inharmonic overtones. Let's do a frequency, fine frequency, and see what happens. Sounds to me like a bell, except for the envelope is incorrect for a bell. So let me modify the envelope of the operator 1. Let me select operator 1 to be more bell-like. Go to edit, and the rate 1 is going to be sharp attack. Okay, that's good. Put it on 96 or something. Go to rate 4, which is the release time. Starts sounding like a bell. Now the envelopes of the operator 1 and 2 are a little different, so let me just copy the envelope from operator 1 to operator 2. I'm going to go to EG, envelope generator copy from operator 1 to 2. Yes. Maybe a little too much. The release time. And it basically sounds like a bell. Okay, let me actually show what I mean by the carrier and modulator interaction. Let me just start showing graphically what the sine function looks like. So it corresponds to the sine wave. So let me just say sine x graph. This is the base sine function. That's what a sine waveform looks like. And let me add to it the modulator now. Let me modulate this wave. So I'm gonna say, instead of saying sine x, I'm just gonna carry this up, I'm gonna say sine. I'm gonna open parentheses, say x plus sine x, close parentheses. So this is what the interaction between the modulator and the carrier are. The second sine x function is the modulator in this case. So let me graph this and see what it looks like. See that the sine wave that we had previously, it started to bend a little bit towards the left side, a bit about an angle. So it's getting closer and closer to a sawtooth wave. Now let's see what happens if I change the frequency of the modulator to make it the frequency of the modulator twice as high. So instead of having sine x, let me just say sine 2x. Close parentheses. See what happens. So that's basically what happened when we got the clarinet sound. That's what will happen because the ratio of the modulator to the carrier was 2:1, and that's what we have in this case. Let me graph this now. You see, this wave gets closer and closer to the square wave right now, and that's what the clarinet wave is close to. It's close to a square wave.